so hi everyone. So today we're going to check the second requirement on flexural members. And this is the strength or the shear strength on beams. So after checking the adequacy or considering the first requirement on steel beams, which is the flexural capacity, so we need to check also the second requirement, yung shear strength on beams nga. Okay? So the applied shearing stress may be coming from the maximum shear stress, FB, and that could be horizontal shearing stress, and that would be VQ over IB. And we have direct shear stress also, which is concentrated on the web part of an I-shaped section, and that would be shear force divided by the area of the web. Okay, so if you will look at the shear diagram, okay, so this is the shear strength diagram of an I-shaped section. So this is the horizontal shearing stress, while this is the direct shear stress. Okay, so as you can see that the shearing stress or the shear stress on the web is a lot greater than that of the flanges. So that's the reason why whenever we check the shear strength on beams, we're focused on the shear strength of the web. Okay, so as per AISC specification on shear strength, okay, so the design shear strength Phi Vn and the allowable shear strength Vn over ohm shall be determined as follows. Okay, so as per LRFD, okay, so as per LRFD, the VU should be less than or equal to the Phi Vn. Okay, so the same lang din naman siya ng yung design strength Phi Bn should be greater than or equal to Vu. So ganyang format kasi yung ginagamit natin dati, no? Wherein yung Phi Bn is the design strength and yung Vu is the ultimate shear force or shear strength. Okay? Now, yung Phi dito nagva-vary depende kung anong klaseng section. Tapos yung Vn natin can be calculated based from the next slide. Tapos yung Vu naman natin, ito yung ultimate or the maximum factored shear or shear force in beams. Shear force sa beam. So, ito yung maximum shear force. No? So, unlike pagka-concrete, diba, ang VU sa concrete is at D distance from the face of the support. So, wala tayong ganun D distance. Okay? So, sa steel, ang VU is the maximum shear force. And yung Vn, yung nominal natin, yung nominal shear strength natin depends on the limit state that it will experience. So these are the following modes of failures. It could be web shear yielding, it could be web inelastic buckling, or it could be also web elastic buckling. So as you will notice, all of them are possible failures on the part of the web. Okay? Okay. So for the nominal shear strength V sub n, okay, it is given as Vn is equal to 0.6 of Fy times area of the web times C sub V. Now, so yung 0.6 of Fy is the shear yield strength of the steel. Yung Aw is the area of the web. Okay, so area of the web. So how is it ba? Diba, let's say you have this I section. Okay, so let's say you have this I section, let's say a wide flange section. Okay, so ito yung pinaka area lang ng web ang concern natin. So basically, itong portion na to. So kumbaga, yung resistance ng mga flanges against shear is being neglected kasi very minimum lang yon. So di ba ito lang yung area ng wide flange na nagre-resist ng shear, and that would be the overall depth D, di ba? Ito yung D times thickness of the web. So yun yung rectangular area, yun yung area of the web. So D times TW. So ito yun. Tapos yung C sub V, that is the modifier that accounts for buckling behavior of the web. Or sometimes it is defined as the ratio of the critical web stress to shear yield stress. And sometimes it is called as the web shear coefficient. So basically yung CB nagbabago depende dun sa limit state na pwede ma-experience nung beam natin against shear. Okay. Now, so again, so these are the values of the web shear coefficient. Okay, C sub B. The values of CV depends whether the limit state is web yielding or web inelastic buckling. Okay, so nagbabuckle din yung web, or it could be a web elastic buckling. So these three limit states can be identified by checking these ratios, the following ratios. Okay, so for case 1, this is applicable for hot rolled. So hot rolled tapos I-shape siya. Tapos you have to check this condition. Yung H over TW ratio niya should be less than or equal to 2.24 square root of E over Fy. So basically, all of the variables are properties of the section. And basically, they are always given. So kapag ka na-satisfy yung equation na yan, that fall under case 1. And then for case 1, the resistance factor as per LRFD is equal to 1.0. Then the corresponding ohm or the safety factor for ASD is 1.5. Again, the product of ohm and the product of phi is always 1.5. Kaya 1 times 1.5 is 1.5. Tapos yung C sub B na gagamitin natin dito would be 1.0. Actually, yung case 1, that is the best section against shear. So usually, if the section comes from the steel manual, usually it complies with this under case 1. Okay? Now, kapag ka hindi na-satisfy yung condition for case 1, yung given equation na yon, yung H over TW less than 2.24, you proceed to the next case, which is case 2. Case 2 is applicable for all other doubly and singly symmetric shape. Pagka doubly symmetric shape, yun ibig sabihin nun, symmetrical siya about X at the same time symmetrical din siya sa about Y. Pag sinabing singly symmetric, isa lang yung axis of symmetry niya. Example niyan is channel. Okay, so channel is an example of a singly symmetric shape. So yung LRFD, as per LRFD, resistance factor niya raw is 0.9. Tapos yung ohms niya for ASD is 1.67. Okay, so nare-reduce, ibig sabihin. Tapos yung C sub V shall be determined as the following. Okay, so yung case 2.A, you have to check this equation. If it is satisfied, the CB would be 1.0. So meaning to say, there is no web instability on the beam, in the beam. Okay, so CV is equal to 1 din. Now, okay, so yung next natin is, what if, ito yung case 2B. Okay, so yung case 2B. For case 2B, you have to check this equation if it would be satisfied. So if the H over TW is greater than 1.1 square root of KVE over Fy, but less than 1.37 square root of KVE over Fy, so these are empirical equations, no? Kapag yung H over TW ratio mo is within that limits, the CB can be calculated given by this formula. Okay? And that means inelastic web buckling occurs on that beam. Now, for the third case, kapag yung H over TW mo is greater than 1.37 square root of KVE over Fy, ito naman yung corresponding KV value mo na gagamitin. And that means elastic web buckling occurs on our beam. These equations, these ratios or limits are being developed based from the different experiments done by the experts. Okay, so doon nila na observe that different types of web failures happens based on the H over TW ratio. Okay, so again, yung H is pagka standard section, H is equal to D minus 2K, di ba? Diba? So pagka wide plan section, H is equal to D minus 2K. Okay? Tapos pagka built up naman, H is just equal to D minus 2 thickness of the flanges. Okay? So tapos of course, yung TW is the thickness of the web. Okay? So ganyan ang pagkuha ng ano. Now, but what is this KV? Diba? I don't know if you have noticed this KB. What is that kV? Okay. Yung K sa V, okay, so this is K sa B. That is the value of the web plate buckling coefficient. K sa B ang tawag doon. Then the web buckling coefficient KV can be determined as follows. So we have two cases here. Case A is kapag kayong stiffened web with H over TW less than 260, the KB would be equal to 5. Except for the step of the T shapes where KB is equal to 1.2 naman. Then for letter B, case B, for stiffened webs, KB can be calculated using this formula, plus 5 over A over H square. Okay? So, and while KB would be equal to 5 kapag ka naman yung A over H mo is greater than 3.0 or A over H is greater than this value. So you just have to check with these limiting ratios, no? So for us to able to identify the value of the K sa B. So take note na yung A na ginamit dun sa equation is the clear distance between transverse stiffeners. Ano yung sabihin nun? Okay, so ganito. Halimbawa, you have this section. Okay, so let's say you have this I section. Okay, so tapos, let's say this is the length of the section. No? So ito yung wide flange beam natin, kunwari. Okay. Okay, so ganyan yung section natin. Now, kapag ka yung web natin, yung web mismo, yung web part ng beam natin is medyo mahina against shear, so we could provide web stiffeners. So web stiffeners are rectangular plates that are placed dito sa part na to. So ano ba? Maglalagay ako ng web stiffener diyan. So these are steel plates. Ipinapasak mo diyan sa loob. Na pinapasok natin sa loob. Diba, may web stiffener ako diyan sa harapan, tapos maglalagay ulit ako ng web stiffener dito sa loob. I mean on this part. So web stiffener uli ako dito. May plate ako ilalagay diyan. Tapos meron din ako sa likod. Yung distance between these web stiffeners, yung spacing nilang dalawa, yan yung tinatawag nating small letter A. Okay, so ito yan yung small letter A. The clear distance between transverse stiffeners. Transverse stiffeners are also known as web stiffeners. Okay? So let's have this example. Okay, sample problem number 7. It is actually the same with sample problem number 5. So if you will remember yung sample number 5, parang pina-design sa atin yung beam against flexure. So yung final answer natin doon was I think pina-check yung adequacy natin, pina-check yung adequacy ng beam na to against flexure. So this time, we're asked to check for the adequacy of this W section, W30 by 116, against shear naman this time. So again, so this is the same beam. We have a simple beam with uniform load dead and live load, service yan. Tapos we have a service concentrated dead load of 200 kN applied at 4 meters from the left support. The full span of the beam is 12 meters and the section is W30 by 116. So we're going to check for the adequacy against shear. Okay, so paano natin gagawin yon? So we will be checking it against shear. Okay. So that is the beam. Okay. So the first step is how do we check for the shear requirement? So we have to check if the actual shear stress or the shear strength or the ultimate shear strength is less than or equal to the design shear strength. Okay. Yung VU, that is the reaction on the left actually. No, kasi if you will draw the shear diagram of this beam, you will find out that the maximum shear is located at the left hinge support. Okay, so yun ang ginawa ko. So I solve for the reaction on the left support kasi that corresponds to the maximum shear. Okay, so solving for that, it give us 604 kilonewton. Okay, so yun na yung VU. Now next, how do we solve for the design strength? VN. Okay, so yung VN, as I've discussed kanina, it's given as 0.6 of Fy AW times CV. So yung FY given naman, no, FY ng beam, yung AW yun yung area ng web. Alam mo naman yung depth at saka thickness ng web ng wide flange section, ng section na given. Tapos yung CV alamin na lang natin. Okay, for the value of the CV, since the given section is hot rolled, so it complies with the first case, okay? So case A. So we need to check for H over TW. H over TW, check if it is less than or equal to 2.24 square root of E over Fy. Okay, so substituting values. So yung H natin, this is D minus 2K divided by TW. And check natin if it is less than or equal to 2.4 square root of E. Yung E na ginamit ko, 229,000 KSI. Kasi yung Fy given was 50 KSI, grade 50 kasi. So calculating for these values, it satisfies naman the equation. So therefore, it fall under CB, case 1 ng CV. So ano uli ang CV value pagka case 1? Okay, so if you could recall, the resistance factor under case 1 is 1.0. At the same time, the CV value is also equal to 1.0. So therefore, we could solve now the V sub n as 0.6 of Fy, area of the web, times C sub B. So I just substituted the values of Fy. Kaya lang yung Fy na ginamit ko is 50 KSI. I converted it to megapascal, kaya may times 6.9 dyan. Tapos yung area of the web is depth, 762, times thickness of the web, 14. Then yung CV natin is equal to 1. So from there, we got V sub n equals 2264 kilonewtons. Ayan, so after knowing V sub n, we solve for the design strength by multiplying it with phi. Kaya lang yung phi natin is equal to 1 din. So therefore, lumalabas na yung Vn is just equal to the same with phi Bn. Okay, so as you can see, yung phi Bn natin is 2,200, tapos yung Vu natin is only 604. So ibig sabihin, our design strength is even more than enough, diba? Greater than. So triple, no, more than triple ng V sub U natin. So therefore we can conclude that the beam is also safe on shear. Most of the time, whenever we check shear requirement, kapag yung beam pasado sa flexure, most likely pumapasa sila parati rin sa shear. Okay? Now, my question is, anong klaseng beam yung pwedeng pumasa sa flexure pero bagsak sa shear? Okay, so anong klaseng beam kaya 'yon? Again, anong klaseng beam kaya? Okay, anong klaseng beam kaya yung pwedeng okay sa flexure pero not okay sa shear? What kind of beam kaya 'yon? Okay, so that is possible for the case of corbel. Corbel. Okay, ano ba ang corbel? Corbel are actually short cantilevered beam. So, halimbawa, ito yung fixed support. Tapos may beam ka dyan. Kaya lang yung beam natin short lang. Maikli lang. So, ganyan lang. Wide flange beam din siya. Ganyan. So wide flange beam. So, ang corbel, usually, ginagamit kasi yan as parang suporta lang. Tapos on top of it, dun lang natin ilalagay yung beam. May beam dito sa ibabaw. Okay, so yung length ng beam na green, perpendicular sa screen. So nakaganyan yung beam na green. Okay, so di bali yung kulay purple na short beam, patungan lang siya, tungtungan lang siya. So ang tawag doon corbel. And pagka ina-analyze mo yung corbel, diba, ang span niya very short yung span, tapos cantilevered pa siya. Tapos yung load na kinakarga niya is the reaction coming from the green na beam. So ibig sabihin, napakalaki ng shear force kapag ganyan. No? So for that case, usually ang nag-govern diyan is shear. No? So dinidesign ang mga corbel usually against shear kasi doon siya nagfe-fail. Okay? So yan. So yan yung example natin for shear. Okay. Okay, after shear, so okay na tayo sa shear, no? So yung shear, para mabilis lang ang shear, no? Parang susundan mo lang yung mga equation set by the code on determination of C sub B. Titingnan mo kung saan siya magko-qualify doon. Okay, so let's move into the third requirement on steel beams. And that is deflections. Okay, deflection on beams. Again, yung flexure at saka shear, these are two strength requirements. Yung deflection naman is serviceability. So again, so in addition to being safe, a structure must be also serviceable. Serviceable structure is one that performs satisfactorily, not causing any discomfort or perceptions of unsafety for the occupants or users of the structure. So hindi naman siya ganun kadelikado yung deflection. Kaya lang, pwede siyang magbigay ng alarm or panic para dun sa mga occupants at para kabahan sila. Parang hindi to yata safe yung building na to kasi lumulundo siya ng mga 4 inches. So parang hindi yun nakakapanatag ng loob, di ba? So to avoid those perceptions, sinasama na rin natin yung deflection sa pagde-design, and that is part of the serviceability. Again, deflection is a serviceability limit state, not one of strength. So therefore, deflection should always be computed with service load. So remember this. Okay? So dapat daw, it should be computed on service loads pagka deflection yung chine-check natin. Meaning to say, hindi na natin kailangang i-factor yung dead load tsaka live load. Wala na tayong factored loads here. Service loads lang ang i-consider natin. And here is the table for the deflection limits. So these are the maximum live load deflections based, depende kung anong klaseng member. Maximum dead and live load deflection. Ito naman, hindi naman natin nagagamit yan kasi wala naman tayong snow dito sa Philippines. Okay, so for roof beams, supporting plaster ceiling or supporting non-plaster ceiling or not supporting any ceiling, so these are the allowable deflections na roof beams. And pagka floor beams naman, ito naman yung maximum live load niya, L over 360. Pagka dead and live combination, it's L over 240, wherein L is the span of the beam. So in terms of deflection, in checking deflection, syempre kailangan alam mo yung mga pagkuha ng actual deflections. Kasi dapat yung actual deflection should be less than or equal to the allowable deflection. Okay, so yung allowable deflection, ito yun, yung nasa table. So ang problema natin, paano pagkuha ng actual deflection? So theory of structures. So pwede kang gumamit ng double integration method, area moment method, conjugate beam method in solving for the actual beams, actual deflection of these beams. Unless madali lang ibigay sa inyo. Halimbawa, simple beam with uniform load. Ito, yan yung pinaka-common. So dapat memorize nyo na yan, ha? That the deflection on simple beam with uniform load would be 5 WL to the 4th over 384 EI. So dapat alam niyan. Paano pagka concentrated load? Yung simple beam with concentrated load at the midspan. So that's PL cube over 48 EI naman. Okay? Kapag cantilever beam naman with uniform load. Cantilever beam with uniform load, that is WL to the 4th over 8 EI. Pagka cantilever beam with concentrated load naman sa dulo, sa free end, anong maximum deflection? That is PL cube over 3 EI naman. So dapat lahat ng formulang, 4 na basic formulas na yon ng deflection, dapat nasa isip nyo na yon, no? Okay, kung hindi nyo memorize, okay lang yon. Kaya nyo na bang, dapat kaya nyo i-derive. Kung hindi nyo memorize, dapat kaya nyo i-derive using any of the methods you have learned from theory of structures. Okay, so let's have this example. Okay, so let's have this, let us solve this example. So the sample problem number 8 was taken from sample problem number 6. The same beam lang siya. Then we're asked to check for the adequacy of this W14 by 90 na section against deflection. Okay. So let's see. Okay, so the beam carries a dead load and the live load, and the length is 6 meters. Okay, so from previous problem, we have solved for the dead load of 42.87, and it is given in the problem that the live load is twice the dead load. So that's 42.87 times 2. Then what I did is inad ko lang yung dead load tsaka live load, and the sum of this dead load and live load is 128.66. Hindi ako naglagay ng load factor, no? Yung 1.2 dead load tsaka 1.6 sa live load. Hindi ako gumamit doon kasi deflection yung chine-check ko. Okay. So, how do we check for the adequacy? So, we have to check for this W14/90 against deflection. So, in such a way that the actual deflection calculated should be less than or equal to the allowable. Okay, so looking at the table that we had that I presented to you a while ago. So this is a floor beam, no? The given problem is a floor beam. Tapos we will be considering both dead and live load. And as per the table, the maximum deflection would be L over 240. Ito. Roof beam siya. Tapos dead and live load yung kino-consider natin. So therefore ito yung allowable deflection niya, L over 240. Okay? So I solved for the actual deflection using the formula, which is 5W L to the fourth over 384 EI. Yung double yung ginabit ko rito, yung total service dead and dead plus live. Tapos yung elasticity is 200,000 megapascal, and the moment of inertia is IX, which was taken from the table, still manual. So the actual deflection was calculated as, ayan, 26.091 actual. Tapos I solved for the allowable deflection from L over 240. L is 6 meters converted to millimeters. Kaya 6,000 over 240, I got 25. So as you can see, the actual deflection is 26 while the allowable is only 25. So therefore, nag-fail. No? So nag-fail yung beam natin sa deflection. Ang kailangan lang kasi 25 eh. Okay, so 25 naging 26. So it failed on deflection. So what you can do there is you change the section. So you may increase the, maybe you may retain W14 pa rin ang susunod ng pipiliin mo. Tapos pili ka lang na mas makapal yung thickness ng web. 'Di ba ang thickness ng web dito, ano ba? Or basta, yun, pwede kang gumamit ng W14 by something na bago in such a way na pumili ka ng section na may mas malaki na moment of inertia. Kasi ang moment of inertia natin dito is 416. So pili ka ng W14 from the steel manual na may mas malaking moment of inertia kaysa sa 416 para lumiit yung actual deflection mo ng 25 mm. Okay, so that is how we design steel beams against deflection. Okay, so that's it. So this is how we design steel beams against shear and against deflection. Okay, so thank you for listening.